Hello and welcome back. We're going to talk about finding equations of sinusoidal graphs. And let's look at a problem. Here we have a function here, a graph or a function. And basically, do you notice some characteristics about this graph? What is significant about this graph? Well, this graph basically has characteristics of a cosine function, doesn't it? And do you understand why it does? Well, look at here. This maximum value of 3 occurs at 0. So we view the graph as a cosine function. And let's look at the equation here. Y is equal to A cosine omega times x. Now, here we have 3, right? Which you recognize what that value is, 3? Because A is equal to 3, and the period t is 1. So again, let's go back to the graph. See? It kind of loops and dips down and goes up, and it goes right back up again. So from here, from this point, from 0 to 1, in this particular case, is the period. Now, if t is equal to 1, we know that this is true right here. T is being equal to 1 here, right? So here's what we have to do. We want to find omega, don't we? We want to find out what omega is. So we have to solve for omega. We have to solve for omega. Omega looks like a W, but it's a Greek letter, small lowercase omega, right? So what we do, we have to what? We have to multiply omega to both sides. And when we do that, this is the expression that we get. 2 pi is equal to omega. So in this case, if we have that, what we have given and what's already been found, we can actually plug the values into the equation and actually have a live equation here. We have the formula, and now it's a true equation because we had things that were given and we had found some other variables here. So with this, with the information that we have found, y is equal to 3 times cosine 2 pi, right, because that's omega, x. Let's do another problem. What is significant about this function here? What do you notice? The period basically starts always at the origin, but now look at how this does. There's a reflection about the x-axis, isn't it? Right? So let's look at this. We have a period from here to there. So the period is 4, right? So basically what we have to do it again is to solve for omega. We solve for omega, and we take omega to both sides, we multiply it to both sides of the equation, we get this expression. And as we simplify this, omega is pi over 2. So since the graph passes through the origin, right, it is easy to see that it's a what? Sine function. But notice the graph is actually a reflection of the sine function about the what? X-axis. As we mentioned earlier, it's a reflection because what? And you'll see in a second what that formula is. For a sine function about the y, since the graph is decreasing near the origin, this requires that A is equal to what? -2. The amplitude is -2 here, right? So, because it's flipped, it's reflecting about the x-axis here. So y is going to equal A times sine omega x, right? And so y is going to equal to what? -2 times sine pi over what? 2x. So basically that concludes the video section on finding the equation for sinusoidal graphs. And we're going to start something new. We're going to talk about another trigonometric function. We're going to talk about the tangent function, which is very, very unique. And I like the tangent function. Actually, I love all of them, but tangent in particular is one of my favorite functions to analyze. It has a period of pi, and we need to only be concerned about determining the interval of some length of pi, right? And the rest of the graph will be repetitious, just like the sine and the cosine function, of course, as it has a particular rhythm at the period, and it continues that rhythm from negative infinity to what? To positive infinity. So the rest of the graph will be repetitious about the intervals on the graph because the tangent function is not defined at these values right here. Negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and so forth and so on. But we will concentrate on the intervals from what? Negative pi over 2 to pi over 2, right? And which is within that length, within that interval length there. And we can construct a table and plot the graph y is equal to tan x, in which here, this is in inequality notation. We have negative pi over 2 less than x less than pi over 2. And we can see how some of the points are raised on the graph. We can show a partial graph of y is equal to tan x with here, negative pi over 3 less than or equal to x less than or equal to pi over 3. So as you see, here's the table that we have, and here is the graph that was constructed, of course. We like to construct a table and actually a partial graph of the function, right? It just actually show how it really, really behaves in a sense, and how it's constructed through the points, right? So we see this graph and this graph here, and also this table, and the table here with the points enables it to be plotted. And when you plot these points, you can draw a smooth line, continuous line through those points. Now let's talk about an important note. This is an important note here. To complete a period now on the tangent function, we need to investigate the behavior of the function. However, we also need to be careful though, because as x approaches negative pi over 2 and pi over 2, that function is not defined at those values, you see. But to determine the behavior of the function, we must use the identity function. You remember what the identity function is? Right? The identity function, tan x is equal to sine x over cosine x. And we'll see how that works as we go along in later videos to come. Let's continue with our important factors here. If x is close to pi over 2, which is actually approximately 1.5708, but remains less than pi over 2, then sine x will be close to 1 and cosine will be positive and close to 0. However, so the ratio sine x over cosine x will be positive and large. Now, let's look at this. The closer x gets closer and closer to what? To pi over 2, the closer the sine x will get closer to 1 and cosine x will get closer to what? 0. So tan x approaches positive infinity. Now, do you recognize this? Now, some of you may not, some of you may, some of you may not. Now, if some of you have been in high school and have taken AP Calculus, you've seen this before. Those who are in college now that's taking trig, you might have seen this before in their AP Calculus class. Those who have taken calculus and successfully passed it, however, but you need to go back and review your trig, you've seen this before. And that is the limit as tan x, limit of tangent x, as x approaches pi over 2 from the left-hand side. So it's coming from it's approaching pi over 2 from the left-hand side. That's what that means. And that will be x, that limit will be equal to infinity. So in other words, the vertical line, x is equal to pi over 2, is a vertical what? Asymptote. Y'all remember asymptotes from your old college algebra and algebra 2 courses? You remember that? Asymptotes, right? So, to the graph of y is equal to tan x, we will see how those asymptotes are arranged. Now, let's look at something else here. The closer x gets closer, the closer it gets to negative pi over 2, then sine x will get closer to negative 1, and cosine x will get closer to 0, and the ratio sine x over cosine x approaches what? Negative infinity. So still we have something here again too with the limit of tangent x as x approaches pi over 2 from the what? Right hand side. So that's going to equal to what? Negative infinity. And here we have, if you can see, like the vertical line of x is equal to negative pi over 2 is a what? Vertical asymptote. So these are our asymptotes here. As you see in red, these are our asymptotes. And of course, your tangent function is drawn in between these asymptotes. Remember, it doesn't touch the asymptote, but it gets closer and closer and closer and closer to that point on the graph, if you will. Now, you can also look at the graph here, look at the, excuse me, not the graph, but the table here, and that can show you how the numbers are actually operating as far as those things getting closer and closer to. Basically, this is the introductory portion of the tangent function and graphing the tangent function, which is a beautiful function. Well, all of them are beautiful, but you know tangent function is very, very unique in its own way. And we will talk about, we'll talk about the properties of the tangent function in the next video. We'll also get into cotangent and cosecant functions as well. So tune in, look for the videos. Hope you tune in. Be looking forward to seeing you real soon.